The truth is out there. I went to the future to find it. Whoa, that was pretty cool. A proof is a demonstration of a statement to be true based on a given premise. In order to believe something is true, you must provide a good argument for that. But what's a good argument, and how good is good enough? Proofs provide the foundation upon which we build our society. Let's take a journey through space and time, logic and reason, and prove the truth is out there. Our first proof is from algebra, and if you can solve an equation, you can do this proof. Suppose I ask you to solve the following equation. 2 times 3x plus 4 equals 56. You might do something like this. First, distribute the 2. Next, subtract the 8. Finally, divide by 6 and get x equals 8. Pretty simple, right? But what if I posed the question to you slightly different? What if I asked you, if 2 times 3x plus 4 equals 56, then prove x is equal to 8. Well, in order to prove something, we have to provide a list of statements and reasons for our argument. So we begin first by stating our equation, 2 times 3x plus 4 equals 56. Then we propose that we will use the distributive property, and when we do so, we will then substitute our equation with a simplified version, 6x plus 8 equals 56. Now, stating something that's kind of obvious here, 8 equals 8, we can use that statement together with statement 3 to do a little subtraction. So we can state the subtraction property and show that we are subtracting lines 4 from 3. Making another substitution, we can simplify our equation to 6x equals 48. Another reflexive property, 6 equals 6, allows us to then divide both sides of equation 6x equals 48 by 6, and using the division property we get our last statement, the one we wanted to prove, which was x equals 8. That's our last statement and reason because that's what we wanted to prove. A logical chain of reasons.
All personnel, please evacuate to the nearest line and report to your supervisor. North gate is secure.
Our next proof is a geometry proof, and a pretty important one at that. But first, a little review on parallel lines. To construct a pair of parallel lines, we must first introduce a third line called a transversal. Using a compass and straight edge, we construct a line AB, and through point A, we will construct another line, which will be our transversal. Since the transversal has now created an angle at point A, we want to copy this angle along the transversal. So, using a compass, I strike an arc through this angle and locate points C and D that cut this, and then decide where on the transversal we want to copy point A. We'll denote it here with A prime. We create the same arc at A prime as we did at A, helping us locate a copy of point D called D prime. We next measure the distance between C and D with our compass and copy that distance above. Now we can mark C prime, and with a straight edge, we can create our parallel lines. We have now created a pair of congruent corresponding angles. Corresponding angles are important in our next proof. And with that, we can identify some other important angle pairs when parallel lines are cut by a transversal. Focusing on the angles highlighted in orange or black, here we have a pair of alternate interior angles, and they are always going to remain congruent. The transversal moves and the Z pattern angles always remain congruent to each other. So we can see how corresponding angles remain congruent as well as we move our transversal. These on orange or in black are corresponding angles like we constructed earlier. And the last pair of interesting angles we can identify are same side interior angles, and those are on the same side of the transversal but interior to the parallel lines, and they always remain supplementary. Recall that supplementary means that they always add up to 180 degrees. So these will be some facts that we can use to help prove some things in geometry, especially what we're going to prove next, that the sum of the interior angles of a triangle always add up to 180 degrees. So we want to prove that the sum of the measures of the internal angles of a triangle are always 180 degrees. Here, angles 1, 2, and 3 always add up to 180. We'll do this by introducing the auxiliary line that is parallel to the base of our triangle. This will set up a set of alternate interior angles that we can work with, and based on what we learned before, alternate interior angles always remain congruent. So pairs of angles 1 and 4 and angles 3 and 5 are both pairs of congruent alternate interior angles. And again, that's because we have set up a pair of parallel lines. Next, we observe that angles 4, 2, and 5 all sit on a line. That is, that we can state a fact about adjacent angles all sitting on a line, and that is that angles on a line are supplementary, so that they will always add up to 180 degrees. That is, that they form a straight angle. Now, by making some substitutions from line 2 into line 3, we arrive at the statement we actually wanted to prove, and that was that angles 1, 2, and 3 always add up to 180 degrees by substitution. That is, the sum of the angles inside of a triangle always add up to 180. Once you have proven something is true, such as this, you can use it as an argument for other more complicated proofs. This next proof involves both geometry and algebra, and it's pretty cool. Check it out. The Pythagorean theorem, a squared plus b squared equals c squared, is the formula relating the lengths of the sides of a right triangle. To prove this, we first start out with 4 copies of right triangle ABC, and we construct a square by connecting the 4 hypotenuses C. Now, we collect the expressions for the internal areas created inside the square and set them equal to the area of the big square that has a side length of a plus b. That is, its squared area is a plus b squared. Now the internal areas are, we have 4 of these AB triangles, or 2 rectangles of length AB, and so we have 2 areas of AB. We also have the area C squared. So the total area of the square, a plus b squared, is equal to the internal areas, c squared plus 2ab. That's our first formula. Next, we're going to construct the same square with side lengths a plus b, but divide the internal areas into squares and rectangles this time. Writing out an expression for the area a plus b squared equals the internal areas, we get a second formula for the area of square length side a plus b. Now we can substitute one of these expressions into the other one, do a little canceling of common terms, and get the Pythagorean theorem, a squared plus b squared equals c squared. Done. We've proven the Pythagorean theorem. Hands down, the Pythagorean theorem is the single most important formula connecting algebra and geometry. This next proof is an example of proof by contradiction. In this example from number theory, we will prove that the square root of 2 is irrational, which begs the question first, what is a rational number? The set Q for quotient of rational numbers is a set of all fractions P over Q, where P and Q are integers that are relatively prime. That means their greatest common divisor is 1. We start a proof by contradiction by assuming that the opposite of what we want is true. Here we're going to assume that the square root of 2 is in fact rational, so we'll let the square root of 2 equal P over Q, where P and Q are relatively prime. Squaring both sides of this equation allows us to write 2q squared equals p squared, and that's going to allow us to deduce something about p squared, or in fact p. That if we can write this as 2q squared equals p squared, then p squared is a multiple of 2. In other words, it's an even number. And that would also imply that p is an even number since an odd squared is always odd. So now, from here we can rewrite p as an integer 2m and substitute into our equation p squared equals 2q squared. That becomes 2m squared equals q squared, after a little bit of simplification. Now, using an argument similar for p squared, we can reason out that q squared and then thus q must also be even. This is where our contradiction comes from. If our assumption started with p and q being relatively prime, that is, a common divisor of 1, then they both can't be divisible by 2. Thus, the square root of 2 cannot be a rational number. Again, if both of them are relatively prime, and then we've shown that both of them are evenly divisible by 2, that's a contradiction. The square root of 2 is irrational, QED. One of our last proofs is pretty intense, and it's not for the faint of heart. This one's called proof by induction. In the late 1700s, child math genius Carl Friedrich Gauss was given the problem to add all the positive integers from 1 to 100. His genius saw a way to add a copy of this sum to itself, which yielded the pattern of 100 copies of 101. In other words, 100 multiplied by 101. This sum is twice what he wanted to add initially, so we divide the result by 2, giving us 5050. We will now prove that this formula holds true for n number of positive integers added up. So we will be proving that 1 plus 2 plus 3 all the way up to n is equal to n times n plus 1 over 2. Proof by induction is broken up into 3 cases. Step 1 is to show that the first case holds true, that if n equals 1, that the formula holds true. Plugging in n equals 1 shows that if we just have one term on the left, it equals 1 on the right. Now, step 2 is to assume that this formula holds true for an arbitrary value k that's bigger than 1. So we write out the formula expanded for k and assume that that is true. The third step is then which is called the induction step, to show that if it holds for n equals k, it also will hold for the next possible case, k plus 1. So writing out what the k plus 1 number of terms would look like, expanded out, and plugging in k plus 1 in for n, we want to show that this formula also holds true. And what we do is we substitute in the assumption that all the first k values will sum to k times k plus 1 over 2. So making that substitution into the series and simplifying some of the algebra on the left-hand side, we can prove that the left and the right-hand side both equal each other. In other words, that the formula holds true for all values k, arbitrarily chosen. This is proof by induction. Congratulations. You made it, and nice job. Now it's your turn to figure it out. Here's a few problems for you to prove. Good luck in figuring it out, and remember, the truth is out there.